How do you compute the inverse of a matrix, assuming it's invertible? So let A be an n by n matrix. So some key facts that we're going to use. 1, A is invertible if and only if the reduced echelon form of A is the n by n identity matrix. 2, every elementary row operation can be achieved by multiplication on the left by an invertible matrix. Right? So what does that mean? That means if I do elementary row operations to take A to its echelon form, I can achieve the same effect by multiplication on the left by E1 first, and then by E2 to do the second operation, E3 all the way up to EK. So A is invertible if and only if U is the identity matrix, the n by n identity matrix. And in this case, A inverse is the product EK times EK minus 1 down to E1. Right? It's the product of the matrices that you had to use in order to do the elementary row operations to turn A into the identity matrix. So now, is there just a better way to record this product, EK minus 1 down to E1? There is. Well, if you notice, what you can do is when you're doing the row reduction, the Gaussian elimination, now instead of just writing down the matrix A, I'm going to write this sort of mega augmented matrix. I'm going to put A on one side and the n by n identity matrix on the other. Now an elementary row operation is going to correspond to multiplication on the left by this E1, by a matrix. We'll call it E1. Right? And so after one stage, I get E1 times A and E1 times the identity. But E1 times the identity is just E1. And then I repeat. With the second operation, I multiply by an E2, and the third by an E3, and so on. And eventually, I'll get to U, and then this EK times EK minus 1 down to E1. So if U is not the identity matrix, then A is not invertible. If U is the identity matrix, then A inverse, or A is invertible, and A inverse is just the matrix that you have on the other side. In other words, if I want to compute the inverse of a matrix A, I construct this augmented matrix A with the identity matrix tacked on. I do Gaussian elimination, and I will get the identity matrix on one side and A inverse on the other. Let's take a look at this in an example. So suppose A is this 2 by 2 matrix, 1, 2, 3, 4. And let's compute A inverse if it exists. So I construct this augmented matrix, 1, 2, 3, 4, and a vertical line to remind me where the divider is, and then the 2 by 2 identity matrix. And I do my elementary row operations. I can replace R3 with R3 minus 3 times R1. This doesn't change the first row. I get a 1, 2, 1, 0, and the second row becomes 0, negative 2, negative 3, 1. And now I want to use this negative 2 to kill off all the entries above. So I do in row 1, replace it with row 1 plus row 2. And that takes the first row to a 1, 0, negative 2, 1. And the second row stays the same, 0, negative 2, negative 3, 1. And now I'm going to take this pivot and scale it to turn it into a 1. Right? So I divide row 2 by negative 2. And then I end up with the identity matrix, the 2 by 2 identity matrix on the left, and on the right is the matrix representing A inverse. So in this case, A inverse is negative 2, 1, 3 halves, negative 1 half. You can always check your work by verifying that A inverse times A is the identity. And we'll see soon that you only have to check it one direction. So here's some shortcuts. Well, if A is a 1 by 1 matrix, with just a 1 by 1 matrix with element little a, then A is invertible if and only if little a is not 0. And in this case, A inverse is the 1 by 1 matrix 1 over little a. If A is a 2 by 2 matrix, A, B, C, D, then A is invertible if and only if AD minus BC is non-zero. And in this case, you can just write down the inverse. It's 1 over AD minus BC times the 2 by 2 matrix D minus B minus C A. So if you'll notice, what do? Well, you swap the diagonal entries and you multiply the off-diagonal ones by a -1. And then you scale the whole thing by a 1 over AD minus BC. So if you notice, there's this term highlighted in yellow. So for a 1 by 1 matrix, it's A. For a 2 by 2 matrix, it's AD minus BC. And this is called the determinant of the matrix. And we'll talk more about that in Chapter 3.